Hello again, oceanography students. So this is the second video that you are watching that discusses ocean circulation that is driven by wind. And this is also the final lecture video that is going to talk about circulation. So you learned about atmospheric circulation, you learned about ocean circulation that is density driven, which we call thermohaline circulation. And then you learned about wind-driven circulation, which includes the creation of the major currents in the ocean and the subtropical gyres. So I'm going to talk about a couple of additional circulation patterns or phenomena that occur due to the wind pushing on the water. And this is not to be confused with wave activity, which we will discuss in next week. Okay, so one interesting thing that occurs from the direction of the wind is actually vertical movement of water. So currents also cause water to move vertically in the water column. Upwelling is where you have deep, cold waters that move up to the surface. Okay, so they move from deep to shallow. And when they do, they're bringing up nutrient-rich waters. When an organism dies, its body sinks down to the bottom and it becomes decomposed, and the nutrients get broken down and end up back in the water. But they end up back in the water down deep. So upwelling will actually bring those nutrients back up to the surface where organisms that are photosynthetic can use them and grow and reproduce, and that basically creates a very productive ecosystem. In contrast, downwelling is where you have water that's at the surface that sinks down deeper. And so you have shallow, warm water that moves down into deeper waters. Now, this is the opposite situation of upwelling in that the area where downwelling is occurring in the surface waters, that is actually going to be low in productivity because there are no nutrients coming up to the surface. Instead, whatever's at the surface is actually sinking down. Okay, so we can have upwelling or downwelling occur due to the direction of currents and also the direction of winds. So coastal upwelling and downwelling occurs due to winds blowing either to the north or to the south along the coast. Now, previously, you learned about Ekman transport, and you may want to revisit Ekman transport before further going on, because Ekman transport is the phenomena that creates the upwelling or downwelling in these situations. Okay, so here we have the West Coast, or a West Coast in North America, or the Northern Hemisphere, I should say. And so you can see the coast here, which is in green, and then this is the water over here. And this big green arrow represents the direction of the wind. So the wind is coming from the north and blowing towards the south along the coast here. Now, what happens is that Ekman transport will basically push the water to the right of the wind direction. And remember I told you with your arrows that you should flip them so that they're pointing straight up on your paper if you ever are trying to figure out which way right and left is. So if you did that with this image here, you would see that right would be away from the coast. Okay, so what happens is that water, instead of just like the sea level drastically going down, going away from the coast, what actually happens is that water from deeper down comes up to fill in the water that is being pushed away from the coast. So I can draw this in another view. Okay, so I'm going to draw an ocean profile. So we're going to be like looking through the ocean. Okay, so here's the coast, here's the seafloor, and then we can draw in the water. Okay, so there's the water. Okay, and here's the wind blowing, trying to show you that it's blowing kind of to the south, coming from the north. And then we can draw in what happens due to Ekman transport. So Ekman transport is going to be to the right of the wind direction. So that actually shows to the left here because the arrow is pointing down. So our Ekman transport is going to be, remember, it's going to be the surface, right? The surface water is going to be moving away. So what happens is that instead of this water the water level just declining right by the shore, instead what happens is water from deep down comes in and fills in that place. So we have what's called upwelling when we have this kind of wind pattern. Okay, so let me change back to my normal cursor really quick. Take that off. Okay, so here is another situation, right? Again, we have the west coast in the northern hemisphere, and the wind is blowing from the south towards the north this time. Okay, so we can see that Ekman transport, again, in the northern hemisphere is 90 degrees to the right of the wind's direction. So that means that the surface water will actually be going towards the shoreline. Now, if you're on a beach, do you think that you have to run away because there's going to be a big wall of water coming towards you? No, that's not what happens. Actually, what happens is the water will run into the land and it will actually go down. So in this situation, we have downwelling. And again, I could draw another view of that by drawing, a ocean profile. Let me go back to black there. Okay, and so here is the coast, here is the sea floor, and I'm not going to change the colors this time, I'm just going to do it in black. So here's the surface, there's the water. Okay, so this is the surface of the water, this is down deep. Here's my arrow for the wind. Okay, now remember that Ekman transport in the northern hemisphere is going to be 90 degrees to the right of the wind direction. So that's going to be in that direction, right? So that means that this surface water here is going towards the shoreline. So instead of just, washing onto the shore, what actually happens is it runs into the land and then it just gets diverted down. Okay, and so in this situation, we end up having downwelling. Now, let's look at what happens in along the east coast in the northern hemisphere. Okay, so here we have land. Now is on the opposite side than what I showed you previously, and we have a wind that's going towards the north. So Ekman transport is going to be 90 degrees to the right of the wind direction. So that's actually going to be away from the shoreline. And what we end up with is upwelling. So again, I could draw a little image here showing you here's the coast, here's the seafloor, here's the water, the surface of the water. Okay, the wind is going this way. So Ekman transport is going to be at the surface of the water, right? So it's going to be 90 degrees to the right. So that means the water at the surface would be going away. And what comes in to fill the water is upwelling. Okay, now here again is the east coast in the northern hemisphere, and this time the wind is going in the opposite direction. So if the wind is going down, if it's coming from the north and going towards the south, then Ekman transport is actually going to be into land. So I can draw that again over here. Here's the coast, here's the water, surface of the water, right? And the wind instead is going in this direction. So 90 degrees to the right of this wind direction would be this way. And again, it's surface water. And instead of, washing up, it's actually just runs into the land and it gets diverted down. So we have downwelling in that situation. Okay, and now what about the southern hemisphere? All right, so remember that Ekman transport in the northern hemisphere is to the right, but in the southern hemisphere, it's to the left. Okay, so in this image here, and both of these images here, we're looking at the west coast in the southern hemisphere. Excuse me. So maybe you could think about, like the coastline of Chile or something like that. So here we have a wind that is blowing from the south to the north. And Ekman transport is 90 degrees to the left, so that's going to result in water moving away from the shoreline, and that results in water coming up from deep down to the surface. So again, I can show you another ocean profile. Okay, so here's the coast, here's the seafloor, here's the surface of the water, and here's the wind. Okay, 90 degrees to the left is going to be like this. Okay, so it's moving away from the shore, which results in water coming up to fill in the water that is moving away from the shore. So that results in upwelling. Over here, with the wind coming from the north and going towards the south, so we have a northerly wind, because remember that winds are named for where they come from. So this is coming from the north. That's why we call it northerly wind. It's going towards the south. So Ekman transport, again, is to the left of the wind's direction. And again, if you took this image and you flipped it around so your arrow was pointing up, you would know that the left would actually be into the shore. So if it's going into the shore, then the water is going to then go down once it hits the land. And so we end up with downwelling. And again, I can show you an ocean profile. So here's the coast, here's the seafloor. Here is the surface of the water. Here is the wind. And 90 degrees to the left of the wind's direction is going to be in this direction. So the water is going to be running into the land, and then it's going to be diverted down. So we end up with downwelling in this situation. And it's really important that you do not attempt to try to memorize anything here. What you just need to know is which way Ekman transport goes, and if the water is running into the land, then it's going to go down. If the water is going away from the land, then you're going to end up with upwelling coming up. So please don't try to memorize, oh, in the southern hemisphere, if we're on the west coast and the wind is going to the south, and this is what happens. That's not going to work out well. You're going to get confused when you're trying to take a test. So really try to focus on understanding and not memorizing, okay? All right, now upwelling can also occur away from the coast as well. So there is upwelling along the equator, and there is downwelling in the center of the gyres. Now, I probably should have put these in opposite orders because the downwelling is easier, and I'm going to refer to the downwelling first. And I just want to change my pointer back to the arrow. Okay, so let's look down here first. So what causes downwelling in the center of gyres? Well, in the center of gyres, as we previously learned, waters converge, so they go together. So if water is running into more water, it's just going to sink down, okay? So in places where water is converging, we end up with downwelling that occurs. And I told you previously that downwelling results in low productivity environments because you're not getting those nutrients up to the surface where they're needed for photosynthetic organisms to basically grow and reproduce and then, get eaten as part of the food chain. So if there aren't nutrients there, then you're going to have a low productivity environment, which means you're not going to have a lot of animals living in that area. And so the opposite of that would be an upwelling environment that has high productivity and does have lots of animals living in it. So in the previous examples that I was showing you, in those areas along the shore, when there was upwelling, those would be great places to go like fishing or whale watching because those environments are really productive because of those tiny little plankton being able to get the nutrients they need to be able to grow and reproduce and then feed everything else in the food chain above them. And we'll talk about food chains later on in the semester. So this is sort of just a little note about food chains right now. Okay, so now let's look up here at upwelling at the equator. This one is a little bit more complicated. So we previously learned that the wind patterns along the equator, you have the trade winds, okay? So, so the trade winds exist because of those circulation cells where you have air at the equator rising and then air at 30 degrees north and south falling. What we end up with is a pattern which are the trade winds between 0 degrees and 30 degrees north and south latitude. Now, what actually happens is that the southeast trade winds actually blow slightly farther north than the actual geographical equator, so 0 degrees latitude. Instead, they blow slightly north of that up to what's called the meteorological equator, which is about 5 degrees north latitude. Okay, now going back to the discussion of not Ekman transport, but Coriolis effect, and then Ekman transport, of course, is that Coriolis effect and Ekman transport north of the geographical equator is to the right, and south of the geographical equator is to the left. So what happens is if you look at this arrow in the direction it's going, then the winds or the waters below this wind is going to be diverted away from the geographical equator, like going away north of it and then going away south of it. And so when you have waters that are diverging or moving away from one another, you're going to have water come up in between that area where they're diverging. And so what we end up with is a zone of upwelling right along the geographical equator. So this is kind of cool because in, most areas along the tropics are fairly low productivity environments, except for places like, where we have coral reefs along coast. But when you go out into open waters, in the equator and the tropics tend to be pretty low productivity. And there's an exception to this, and that is very narrowly right along that geographical equator where we end up with upwelling. Okay, so we can see that upwelling and downwelling is common on the eastern sides of ocean basins. As we can see here, we've got lots of upwelling. We've got lots of upwelling over here as well, and also along irregular coastlines and also along the equator. Now, why is it so common on the eastern sides of ocean basins? So the eastern side of the ocean basin would be like the west coast of a continent, right? You have to think back to the direction of the prevailing currents, right? So the California current is right over here, and it's going from the north to the south. So just like winds, currents can also, cause water to be diverted. So if the water is going down, if the water is going towards the south, 90 degrees to the right of that would be away from the coastline, which would result in upwelling. So that is essentially why we have pretty strong upwelling along the west coast of North America. Okay. Now, another phenomenon that occurs with currents is called the El Nino Southern Oscillation. So this is referring to periods of either warmer or cooler conditions in the waters in the eastern equatorial Pacific. So waters in the eastern equatorial Pacific would be like waters that run along the west coast of South America. So an El Nino is a period of warmer than normal waters in the eastern equatorial Pacific, and La Nina is a period of cooler than normal waters in the eastern equatorial Pacific. So if you look at these images here, they show you maps of the Pacific Ocean, and the water temperature is designated by different colors. So blue is colder water and red is warmer water. So we can see in the image on the top here, we have much warmer water in the equatorial eastern Pacific here. That would be signaling an El Nino. Down here, you can see blue, so that is signaling a La Nina, okay? So let's look at what they are and why they occur. Okay, so with an El Nino occurs because the pressure over South America actually reverses. In normal conditions, you have high pressure over South America, which results in strong trade winds and a strong south equatorial current. Just to remind you, the equatorial current both the north and the south, are moving from the east towards the west. That's the normal direction that the water along the equator is normally moving. So this results then in really strong upwelling along the west coast of South America, which leads to pretty productive waters here. Now, in an El Nino, instead, you end up with low pressure over South America, which results in much weaker winds. So because the winds aren't very strong, and they are weak, what happens is the south equatorial current doesn't flow as fast. And instead, in between the north equatorial current and the south equatorial current, there is another current that is called the equatorial counter current. It moves in the opposite direction from the equatorial currents. So it actually moves from the west towards the east. So if these other currents aren't going very strong, what happens is this one takes over. So it brings with it warmer water from the western side of the ocean basin to the eastern side of the ocean basin. And that results in downwelling conditions instead. So as I just discussed previously, downwelling results in low productivity environments. So El Nino conditions kind of suck for fishermen in places like Peru, where they are going out and fishing and they can't get any fish because they're low productivity environments. The fish aren't there. Okay, this also results in some weather patterns, and so usually when you hear about El Nino, it's in relation to the weather. So with an El Nino, we tend to get more rain along the in California. We tend to get more rain, whereas as you go north, like I used to live in Washington, and during an El Nino, you actually got less rain. Okay, so I want to show you these patterns looking at an ocean profile. Okay, so here is South America, here's North America over here. So this is the seafloor. Okay, so this is what happens in normal conditions. The water is moving away from the eastern side of the Pacific Ocean at the equator. And so because water is moving away from the coast, we end up with upwelling. Now during an El Nino, the water moves in the opposite direction. So it's running into the shore. And because it's running into the shore, that results in downwelling. Now a La Nina is the opposite. A La Nina is really just like normal conditions that are intensified. So normal conditions are high pressure over South America, and a La Nina is going to be very high pressure over South America, and it's going to result in stronger trade winds. They're going to be blowing harder, and that means that the equatorial currents are going to be stronger. Okay, so that means that you're going to have even more upwelling and even more productivity. And what that leads to as far as weather goes is we end up with drought-like conditions in California when we have a La Nina. The reason why is you don't have that warm water to be evaporating and going into the air and creating rain. Okay, so that's it for the circulation lectures. Please let me know if you have any questions, and it is much faster for me to respond if you have questions by emailing me rather than waiting for me to read through the discussion post. If you just have something you're curious about, then it's great to post it in the discussion post. But if you have something that you need answered in order to understand, it's better to discuss it with me during our weekly video conferences or during during my student assistance time or by email. Okay, I hope you have a good day or night.